So now we're going to look at these derivatives that we've been finding for functions, and we're trying to look for patterns as we find the derivatives that will make the derivative easier to find. So first of all, I want to start with, for this function f of x equals x to the fifth, find f prime of x. So when I say find f prime of x, what I'm asking you to do is this kind of process that we've done where we find the derivative of a function. We start with this limit definition and we go through all these processes, things cancel out, and we end up with something, a different function, okay? Now, here's where we're headed with observing patterns. Once we see and understand the patterns that occur in certain derivatives, you will be able to look at this derivative, x squared minus 2, and you will say that derivative is 2x. And you will be able to say that in less than 5 seconds. So all of this work is lurking behind that. We are going to have a pattern that gives us this, but it's a pattern that you don't want to use this pattern without understanding where it came from. So our work today is to really understand this limit process to the point that we will see a pattern and know why the pattern exists and why it works. That's our real goal. So what we're going to derive is called the power rule for derivatives, and that is going to allow us to deal with basically anything that has an exponent. All right, now, so the first thing I would like you to do, though, is go through that full derivation process, even though by the end of this lecture, you will be able to look at that and state the derivative in less than 5 seconds. But that's not what I'm asking you to do now. I'm asking you to show me that you understand the full process, do this limit definition starting with the limit, do this limit derivation starting with the limit definition, and find out what the derivative of x to the fifth power is. Hint, it should be a lot of work. Please pause the video and do that now. All right, I'm going to assume that you have now found the derivative of x to the fifth, so I'm also going to go through it just to make sure that you've got all the details right. So we're going to start by saying that f prime of x equals, and I like to always start by stating the limit definition of the derivative. That's what this is, limit definition of the derivative, because it helps me understand that definition, and also helps me remember it. So it's the limit as h approaches 0 of f of x plus h minus f of x over h, okay? That is the limit definition of the derivative. All right, so that's what we usually call that, the limit definition of the derivative. So it's defining what the derivative is in terms of a limit. All right, now this is so important. We're going to come back to this for every type of derivative that we do. Remember, this is really a slope formula. It's y2 minus y1. The f of x plus h, the f of x are y2 and y1. The denominator is x2 minus x1, where x2 and x2 was x plus h, and x1 was x. So the x's cancel out, and when you do x2 minus x1, you just get h. This is just the slope formula, y2 minus y1 over x2 minus x1. But we want to see it now in terms of the limit as h approaches 0 of f of x plus h minus f of x over h. All right, and that's where our starting point for all derivatives. All right, so for this particular function, that is going to be the limit as h approaches 0 of x plus h to the fifth power minus x to the fifth power over h. And this binomial power is where all the difficulty of this limit definition arises, and it's also where the pattern that will end the difficulty arises. All right? So if I want to do this x plus h to the fifth power and I want to expand that, I need Pascal's triangle, because I don't want to sit there and do x plus h, x plus h, x plus h, x plus h. So we're going to do Pascal's triangle. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you don't know where these numbers are coming from, drop me an email or stop by Flex. All right, there's my numbers. Now, these, by the way, correspond to the 0 power, the first power, the second power, the third power, the fourth power, and the fifth power. All right, we'll look at this actually in more detail on the next page. All right, so these are our coefficients of this expansion. So now I'm going to write that I have the limit as h approaches 0 of, now I have to remember that the powers of x descend, the powers of h ascend, and I follow these coefficients. So I'm going to have x to the fifth plus 5x to the fourth h plus 10x cubed h squared plus 10x squared h cubed plus 5xh fourth plus h fifth. So one thing you're going to notice in the expansion is that the sum of the exponents in each term is always 5. 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4 is 5, and 5, okay? So the sum, that's one way you can keep track of, make sure you didn't lose any of the exponents. All right, but then this is all just x plus h to the fifth, so now I need the minus x fifth. So then minus x fifth, all right, over h. Now here's where we're going to start noticing, I've drawn your attention to these patterns before, but I'm going to strongly draw your attention to them now. How the x fifth always cancels the power that's by itself. The term, let's put it this way, the term that has no h in it is going to cancel, all right? And then I have limit as h approaches 0. Now everything you have left has an h in it, and that means we will be able to reduce it. So that's another one of the patterns, and you know that's not a coincidence. It's necessary. It is implied in this process. Now I reduce all the h's out, so I have limit as h approaches 0 of 5x fourth plus 10x cubed h plus 10x squared h squared plus 5 xh cubed plus h fourth. Now this is limit as h approaches 0 of all this stuff. So now I evaluate by substitution. So I have 5x to the fourth, and I'm going to really like spell this out. It's plus 0 plus 0 plus 0 plus 0. So it's not like I threw these terms away. I substituted 0 for them, and what I end up with is 5x to the fourth. Okay, so that's the derivative. That's what f prime of x. I'll just write that down here so we don't forget what we were doing. And here's what I want to really strongly draw your attention to. The processes that always occur are the cancellation of the terms that have no h, and then the reduction of all the terms that do have h. And then the substitution of 0 for all the terms that still have h. So look, the terms that had no h at all, they canceled out at the beginning of the process. The terms that had a power of h that was greater than 1 kept their h's in the next step. But the term that had h to the power of 1 lost its h. Then all of the terms that contain h become 0. Therefore, the only term that survives this process is the second term in the expansion. The second term in the expansion is the only one that survives the process, because this one's going to cancel out, and these ones are all still going to have h in them at the end, so they're all going to be 0. This is the only one, the one with h to the first power. We could say the term that is linear in h is the only one that survives the limiting process and in fact determines the limit. So in our next video, we will look at how that enables us to look at this function and say the derivative is 5x to the fourth. It requires hardly any thought at all. All right, we'll see that soon.